Alright, in this screencast we're going to cover two of the trickiest examples for the unit on torque and equilibrium. So here, what this is supposed to be is a ladder. That's what that diagonal thing is, where the person standing near the top of the ladder. The ladder is 7 meters long. I'll add that here. The ladder is 7 meters, and it's also 25 kilograms in mass. It makes an angle of 41 degrees with the ground, and it has a person on it. This person is 45 kilograms. The ladder makes no friction against the wall. We're going to assume it's frictionless, and what is stopping it from sliding away then is friction provided by the ground. So at the bottom then, what we have is we will have a force of friction. One thing to keep in mind is the forces. So we know there's going to be the force of the person here, there is the center of gravity or the mass of the beam here, there is the force of friction as I mentioned, but there's also going to be another force here, which is a bit different than other questions you've done. There's a normal force. Because friction isn't providing any force on the wall, then the normal force on the bottom has to actually support the weight of the beam and the person. That total mass is supported right there. So the normal force is very important for this question. So the first thing that we should start with, as always, is set up a free body diagram. And so because we're looking at the left and the forces on the left and what's going to happen, we actually set up a pivot on the right. Even though it's frictionless, we're not worried about what's happening on the right. We want to see what are the forces on the left, on the ground and so on, that is going to stop this ladder from sliding. So if I label some of my forces, I have force of friction here, and that's at 41 degrees. I have the force of gravity on the ladder. Now that, if I imagine this as a right triangle here, like that, if that's 41, that means this angle here must be 49 degrees. And if I picture this as a right angle here, something like this, then if that's 41, then this normal force, that has to be 49 degrees in here. Now we have the mass of the person, and because it's the same as the force of gravity in the ladder, that's also going to be 49 degrees, and that's going to be 45 times 9.8. And so let's take a look at our start. Clockwise torque equals counterclockwise torque. As always, any rotational equilibrium questions, that's what you want to start with. So we write things out here. We have our force of friction times sine of 41 degrees, and this is 7 meters to the pivot, plus 25 kilogram mass of the ladder, times 9.8 meters per second squared, times sine 49 degrees, and this is 3.5 meters to the pivot. And see if I have enough space here. I'm just going to put this down here. Plus, I have 45 kilogram person times 9.8 meters per second squared, sine of 49 degrees, and that's 2 meters from the wall of the pivot, and all that is equal to 70 kilograms times 9.8 times sine of 49 degrees times 7 meters. So what we have then for this first one, we have force of friction that is going counterclockwise. We have the mass of the bridge here. This is going counterclockwise. Then we have the mass of the person that is going counterclockwise. And the only one going clockwise here in this case, that is the normal force. And so it's going to be 70 times 9.8 sine 49, 7 meters to the pivot. So if I simplify things here a bit, I get 4.592 times force of friction is equal to 3,624.11 minus 647.16 minus 665.65. And if I solve for force of friction, that works out to 503 newtons. Alright, and the second of the examples that I'm doing is another one similar to what we've done before. This one has a little bit more angles, and so it could be a little bit trickier. And so we're adding this here. So what we have is a beam. The beam is actually up diagonally, and so it's attached to a wall. And this is supposed to be your wall over here on the side. I know, very straight. Oh well. And so it attaches there on a hinge, and if anything would happen, it would pivot right there. It makes an angle of 35 degrees with the wall. The beam is 8 meters long. It's 14 kilograms, and it has a cable that makes 90 degree to the actual beam, and it's attached to the wall. That's attached 2 meters from the far end, and there is a 6 kilogram mass suspended from that beam 1 meter from the far end. So what we are looking for is the tension in this cable over here. So as always, anytime we're dealing with forces, it's always a good idea to do free body diagrams, especially with torque. Very important. So let's say this is my pivot. Here's our beam. So I have one force here. I have this force. One nice thing about that one, it's perpendicular, so I don't have to worry about angles. And I have this force here. Now, as far as angles, if you imagine parallel lines, then the alternate anterior angle rule says if this is 35, then this angle here is 35, and that angle is 35. So for our forces then, being pulled down with gravity, those are 35-degree angles. And so if I go clockwise torque equals counterclockwise torque, and maybe I'll finish labeling my diagrams here. This is my tension, and my tension I know is going to be 6 meters from the pivot, and I also have the 14 kilogram mass times 9.8, that happens here, and then I have the 6 kilogram coming down here. So clockwise torque equals counterclockwise torque, and I'm saying going clockwise is the tension from that cable. Tension times, hang on a second, there is no angle, so let's get rid of the sign there. Tension times 6 meters to the pivot, and that's going to be equal to counterclockwise. Now counterclockwise will be 6 kilogram mass times 9.8 meters per second squared times sine of 35 degrees, and that is 7 meters from the pivot, plus 14 kilograms times 9.8 meters per second squared times sine 35, and that is 4 meters from the pivot. So if I simplify here, I will have 6t is equal to 236.08 newton meters plus 314.78 newton meters. And we work this out, and tension works out to 91.8 newtons. And that's the end.